way back again, right? So when math wasn't so complicated and integration was so complicated, right? Oh yeah, and triple integrals is a pain. That's where even I get a little tricky when it comes to it, but we'll get there. Don't worry. So the question becomes, what if R, our region R, is not a rectangle, right? If it's a rectangle, everything's perfect, everything's beautiful, everything makes sense. But life isn't perfect, right? R is not always going to be a region, a rectangular region. It could be like that, for instance. What if R is some just blob, right, itself, right, or a curvature itself? Okay, so we actually did this in general calculus, and it kind of looked like this. So we want to integral with respect to a to b of a curve. Well, let's say this is f2 and f of 1, right? So when we set up this integral, if you guys remember, it's top minus bottom. So you do f of 2 minus f of 1, and you integrate with respect to a to b. Right, that's what area between two curves. That's what we called it. Okay. And same thing when it came to respect to y. You just change your bounds because it looked different, right? So we had two curves, f2 and f1, and your cutoffs were here from D to C. So this time we couldn't integrate with respect to x. We had to change the bounds to y. But the same process was applied, right? We go integral from C to D of f2 minus f1. So in this case, this was dx. In this case, this was dy. Now that same process is applied in 3 dimensions. Okay. So we have some surface there, and we want to take the integral over the general region. So all we're going to do is transpose it to the x and y plane. That's going to be a region D instead of R. We're going to integrate of. Okay. But again, we're always going to be dealing with in terms of one variable, and again, keeping the other variable fixed. So the same rules apply when it comes to integration. The only thing is our bounds of integration is going to be different depending on the situation at hand, because just like here, our bounds are different depending on what we did, right, in terms of dx or dy. Okay. Unfortunately, when it comes to double integrals, we have more different types we can have. Okay, so the first type of way is the easiest way, is a type where x is fixed, so kind of like we have here, and y has bounds of respect to x. Okay, so y is bounded by a region in terms of x, so two different functions. So an example will kind of look like this. So as you could tell, we still do that same concept as top minus bottom. The only difference, instead of saying top minus bottom as our integral, that's our actual bounds themselves. So in that case, this format is, almost identical. So now we go on to situation 2, or type 2. And type 2 is the exact same format as we have here. So the type 2 region is basically just respect to y. So now y is bounded by values, and x is in terms of y itself. Okay. And we would do the same thing. We do top, or in this case, right minus left, and that would be the bounds itself. The right and the left will be on the bottom of our integral. Now, there's technically 3 different types, but we're only talking about for now the first 2 types, because that's just harder itself, just to identify which situation we're actually in, right? Even though there's only 2 types so far, identify what would be the best situation is still harder than you may think, right? Just like first integration. Is it easier to integrate with respect to x or y, or change my bounds and all the fun stuff, right? That's where everybody gets tricky, and all hell breaks loose. But we're going to try our best to figure this stuff out. Okay. Okay, so let's try the example. So find the integral over the region of D, x plus 2y dA, where D is the region bounded by y equals 2x squared, y equals 1 plus x squared. Now, in my opinion, what I suggest you do is just draw it to see what's going on as best you can. Some of these are too difficult, but the good thing is it's only x, y, right? So it's not in 3 dimensions yet. It's just a nice 2D model. So just going to quickly draw it here. And we'll just, just graph both graphs. So first we'll graph this one. So y equals 2x squared. So we'll just do, plug in 0, you get 0. Plug in 1, you get 2 out. You plug in 2, you get 4, you get 8 out, so way up here. So just shoots up, right? It's a parabola. And same thing on the other side. So this is y equals 2x squared. On this side, it's the same parabola, right? But it's up 1. So it starts here. So x equals 0, we get y equals 1. If x equals 1, we get 2. So it actually crosses here. And does that. And the same thing on the other side. So what we're looking for is our region D is this slivers right here, like this fancy V-ish here. Now it's our job to figure out, are we in type 1 or type 2? Okay. So we have type 2 up here. So type 2 means we have region from here to here. We have, and only in terms of x itself. So there's a curvature here. There's no way I can go from one bound to the other bound. And a type 1 looks like this. We have a top and a bottom region, and we could fix it from x to from the x values. And that's kind of like what we have here. If you're not really sure what to do, or if you have no idea, you can always do from the bounds. So remember our little rectangle. So if I go this side, because we want to do the easiest, so type 1's the easiest of the two to do. So if my rectangle goes up this way, or my cubic goes up, right, scaling up in 3 dimensions. So if I go this way, so therefore, my x values are bounded from here to there, which is just from -1 to 1. That's good, right? We can bound those. Now, if my rectangle goes from there to there, so therefore, in the y values, the y-axis, I go from 0 to here, right? Or so this function to that function. So, and then remember, this is y equals 1 plus x squared. So it goes from a lower to an upper there, right? Because this is the lower of the functions. So this looks like it's a type 1, which is good because type 1 is the easiest of the two to do. Now you can do a type 2, it'd be much harder. But we want to do the easiest of the two anyways. Because if you do type 2, you're going to go from here to here. And it's actually easier to cut this in half and do that and just double it. And that's why it makes it a little harder to do. The type 1 makes it next easier to do, right? Top minus bottom. Okay, so now that we have that, a type 1 represents only in terms of x, right? So the first thing you got to do, oh, actually, it's already done in terms of x. Good. So y and y. So we're going to go from -1 to 1 as our x bounds. And then our integral with respect to y is just going to be the bottom function and the top function. And now we just plug in our region we're integrating from. Now, again, this one we can't separate because there's a plus in the middle, right? If it was a multiplying x times 2y, then we can split it up like we learned last time. Okay. All right, so this one we just got to do the old-fashioned way. So since it's gonna be a little lengthy, I'm gonna start over here. So okay, first integrate with respect to y. So this is just going to be xy plus y squared, evaluated at 2x squared and 1 plus x squared. All right, so general regions are going to be messy, right? So remember, we're going to plug in each one in for y. So I'm plugging it into here. Okay. So if I plug this into there, I'm going to get x times 1 plus x squared plus 1 plus x squared. That's the first part. Minus, you plug out this in. So 2x to the third plus, that's going to be 4x to the fourth. Very messy, right? Okay. So just for the sake of time, this is what I did. I FOILed everything out. So I FOILed this out, distribute this, and then just simplified everything, right? So, right, foiling, I'll just quickly go over it. Or box method, whatever, just FOIL it out. And then just put everything together. I end up getting something like this. And now remember, after we simplify all that, now we do the integral with respect to x. So this is now the integral from -1 to 1 dx. So we're almost done. Right, take the integral. So now this is going to be x to the fifth over 5 and times -3 minus x to the fourth over 4 plus 2x to the third over 3 plus x squared over 2 plus x. All evaluated at 1 and -1. So plug in 1 everywhere, and then minus plug in -1 everywhere. Again, just for simplicity, right? I'm sure you guys could do that. Just, eventually I could just think I did it right. I get approximately 2.13 after you plug it all in. Questions there? Yeah. More examples. Okay. So find the volume of the solid that lies under the surface z equals x plus y squared and above the region D in the xy plane with y equals 2x and y equals x squared. Okay, so same thing. I'm just going to quickly draw, figure out what this region is going to look like. Okay, so they both hit 0. So I'll make this blue, and I'll make this black. So x equals 1, y equals 2. So it's just going to shoot up this way. And this is our parabola. So x equals 1, y equals 1. x equals 2, y is up to 4. So it's a nice parabola going. Yeah. X equals 1. Yeah. Like that. Okay. So if you're wondering where they cross, right? So that somewhere where they're going to cross, we could just set them equal to each other and see where our balance is going to be. So we have 2x is equal to x squared. So that makes sense, right? X equals 0. So 2. So it hits it at 2. All right, perfect. So it hits it right there and there. Oh, sorry, x equals 2 out here. So when x equals 2, oh, so 0, 0, so 0, the 2 is going to be our balance for x. Now, again, same thing. Is this a type 1 or a type 2? Okay. So if it's a type 1, we can, or actually, here, let me show you. This is going to be a region we're looking for. So this is our D region. So again, if it's a type 1, that means I can find my rectangle looking like this. And x is always going to be from those portions there. So notice this is exact same as the last example, which is great because it's just half of it. It's just half of what we have here. So looks like it's also a type 1. Ooh, nice, right? So this is a type 1. So therefore, we have our bounds. So x goes from 0 to 2. So this is a little farther. My picture's a little off. And then y goes from lower to upper. So the lower is going to be x squared. And then the upper is going to be 2x. So our integral is going to go from 0 to 2 and from x squared to 2x of our function, our surface. dy dx. Okay. All right. So respect to y first. So this ends up being x squared y plus y to the third over 3 evaluated at x squared and 2x. So now plugging in 2x into here, that gives me 2x to the third plus 8x to the third over 3 minus, plugging in x squared, it's x to the fourth, plus x to the 6 over 3. So we could put these together. Oh, actually, can we put, oh, yeah, put these together. These can't put together. So I put these together. It's a little easier. This is going to be a 3, and this ends up being 6. So that gives you 14. So we have 14x to the third over 3 minus x to the fourth minus x to the 6 over 3. And we take the integral from 0 to 2 dx. Okay, so doing it one more time. So we get 14 thirds integral, and it's going to be 4. So times another fourth here. Just do it separately. Minus x to the 5th over 5 minus x to the 7th over 3 times 7 on the bottom. Evaluate it at 2 and 0. Okay, lots of stuff happening. So let's see. So I actually don't have this answer. So 2 to the 4th times 14 divided by 12. So this first part I get 18 point, let's say 67 minus 2 to the 5th divided by 5, 6.4, and minus 2 to the 7th divided by 21. So you get approximately 617. Yep. So far, so good. Okay. Now let's go over a little hard one. I put hard for a reason. Yep. So find the volume of the tetrahedron bounded by the planes y equals 0, z equals 0, and x equals 0, and y minus x plus z equals 1. Okay. So let's first rewrite this in terms of z. So just bring everything else except the z over, right? Okay. So what's going on here? Okay. Now we talked about how to draw similar stuff, right? If we just do the x-intercepts of each case. So if I just want to draw this in 3 dimensions. So if x and y are 0, therefore z equals 1. There. If y and z is 0, therefore x must be negative 1. So x is on this side, negative 1. And then finally, if these two are 0, then y has to be positive 1. So this tetrahedron kind of looks like this. Okay. So that's what it kind of looks like as best we can, right? So what we're going to do is to make it easier for ourselves to look at, because we want double integrals here everywhere, we're going to transform this only to the x and y plane. Okay. So what I mean by that is I'm going to transpose this to only look at this plane right here. Okay. Now notice we're in the negative x values here, right? There's no positive x values, so I'm going to make my x, y values go this way instead. So this is going to be the x, this is going to be the y. So if y equals 1, y equals negative 1. So this is our region we're looking at. So this is our D region. Okay. All right. So good thing is we can still do a type 1. You can actually do a type 2 as well. And actually both of these will actually be the same. So the same amount of work no matter what. So if we do a type 1, x is going to go from -1 to 0. But what will y go? So x or y goes from 0, but to what value there? Right? Because it's a line here, it's not actually going to go into 1. So this is the only part where it makes it hard, is not only just graphing the tetrahedron, but also figuring out what our bound is for y. So to do so, all we have to do is, well, what is the line that goes through -1 and 1? Okay. So this goes back to old school, right? So if I have the point -1, 0 and the point 0, 1, find the equation of a line. So slope, so x1, y1, x2, y2. So x2, so y minus 0 over 0 minus a -1. So slope is 1. And our y-intercept is 1. So this is y equals 1x plus 1. Right, so this is the line there. So y goes from 0 to the line x plus 1. Right. So now we have our bounds. We can now actually integrate. So x goes from -1 to 0, and then y goes from 0 to x plus 1. Of 1 minus y plus x dy dx. Okay. All right, so integrating respect to y, same format, right? Nothing really changes there. So integrate respect to y minus y squared over 2 plus yx. Evaluated at 0 and x plus 1. Okay. Then the good thing is 0, you plug in 0, just goes away, which is nice, right? So we're just going to plug in x plus 1 everywhere we see y. So it's going to be x plus 1 minus x plus 1 squared over 2. And then x times x plus 1. Okay. So I'll distribute here. This gives me 2x plus 2. Therefore, I could add these together. So that's going to be 3x. So I'll have 3x plus 3. Oh, no, this is x2x squared when I talk about x. Oh, yeah, 3x plus 1 plus 2x squared minus all of this horribleness. Yeah. So did I do my math correctly? So this is 2x squared x, so that I can only add those together. Yeah, I think that's correct. All right, and now we're going to integrate this with respect to x. So 3x squared over 2 plus x plus x to the third over 2 or 3, the 2 there. I'm running out of space here. Let me get another piece of paper. All right, let me start over from here. So it's going to be 3x squared over 2 plus x to the third over 3 minus, this is technically u substitution, but u substitution, the derivative just gives you 1, so just it's itself. So this is going to be over 2 times 3 gives you 6. If you guys are wondering, that's a shortcut of the u substitution rule. And we evaluate this at -1 and 0. All right, so we plug in 0, everything goes away. That's what's nice. So it's going to be minus, plug in -1, you get 3 over 2 minus 1 minus 2/3 minus, this ends up being 0. Oh, isn't that interesting? All that for what? Interesting. So a little hard question because you have to not only draw it, you have to convert it to either the XY plane and get your balance from there.
Professor?
Yeah.
I had a question about earlier where you multiplied x into x plus 1 in the parentheses. How come you got 2x squared plus 2x?
Oh yeah, you're right. Oh, so she just be x squared.
Yeah,
Thank you.
and plus x, I think.
Oh, okay, so this should be 2x then. Right, so it'd be x squared plus x, and then x times x, 2x. Okay, so everybody else is good?
And then at the end, like at the very end, when you like 3
So
over
then-
2 minus,
Yeah, so then this changes to be a 2 here. And actually, I'll just redraw it.
yeah.
So this should be just be x squared plus x to the third over 3. And this is the same. There you go. Is that right?
That seems like it.
Yeah, okay, good. So now let's see. Now what do we get? So we get 1 minus 1 minus 1/3 minus 0. There we go. Big difference. Now it's just positive 1/3. There you go. Thank you.
Yeah.